Welcome to Physical Hydrology Lecture 13, Part 2 on surface water. We will now turn to the ingredients for conceptually modeling the discharge or runoff from catchments. A model necessarily always is a simplification of reality, and a conceptual model more so, as it singles out a simple physical concept. Therefore, regard the conceptual models or methods that are to be introduced as building blocks or starting modules for building a larger, even better model. This figure shows a cross-section of a river recharged by groundwater, showing the groundwater storage above the level of the riverbed. Assuming the effects of evaporation on groundwater storage as negligible, then, if there would be no more precipitation, the groundwater storage above the level of the riverbed would discharge completely into the river from the onset of the precipitationless dry period at TST to T is infinity, in mathematical notation as shown here. St is the storage at time t above the level of the riverbed in cubic meter. Qt is the discharge at time t in cubic meter per second. As the groundwater storage depletes and the water table lowers, the discharge of the river will gradually decline. We know the discharge Qt at time t after the start of the recession to be equal to this equation. Inserting the equation for Qt in the equation for St delivers this, which can be solved to show that St equals Qt divided by alpha. This equation shows that groundwater flow into a river, which is effluent seepage, is described by a linear relation between the groundwater storage S in cubic meter or millimeter and river discharge Q in cubic meter per second or millimeter per second, with the recession constant alpha with as unit per second as connecting factor. A linear reservoir is defined as a reservoir for which the relation between storage and outflow or discharge from the reservoir is linear, thus with n equals 1 in the more general equation presented in my book for the flow from water-filled reservoirs as shown here. Note that groundwater flow is an important component of base flow and that in many instances the two terms are used interchangeably. Outflow from a groundwater storage reservoir or base flow reservoir may thus be modeled by a linear reservoir model. We can expand the linear reservoir model by combining the just derived equation that links S and Q with the continuity equation or water balance equation for a reservoir. A change in reservoir storage per unit of time, dSdt, equals the input I to the reservoir in cubic meter or millimeter per unit of time, minus the discharge Q, also in cubic meter or millimeter per unit of time, from the reservoir as shown here. More specifically, I is the precipitation rate minus the evaporation rate. The change in storage dSdt is positive when the storage increases and negative when the storage decreases. For a linear reservoir, alpha is the connecting factor between a change in storage and a change in discharge. ds equals dq divided by alpha. Combining both equations gives this equation. How to build a simulation model? We can change this equation to a simulation equation for a rainfall groundwater runoff model, a model that uses discrete time steps delta t to model changes through time, by replacing dt by delta t, dq by delta q being qt plus delta t minus qt, by replacing q by qt plus delta t divided by 2, and by replacing I by I delta t. I delta t is the input during time step delta t. This gives this equation, which after defining beta as this first factor, can be simplified to this equation. This equation constitutes a rainfall runoff simulation model, a model of the reaction of the discharge or runoff in a drainage basin to a precipitation event using discrete time steps delta t. In effect, the end equation tells us that using the concept of a linear reservoir, the discharge Qt plus delta t is influenced by the previous discharge Qt at time step delta t earlier by a weighting factor beta, and by the precipitation minus evaporation during time step delta t by a weighting factor 1 minus beta. This figure shows the effect that using different values of the recession constant alpha has on the baseflow hydrograph modeled with the rainfall runoff simulation model. As expected, a low value of alpha causes the baseflow to react slowly, which is noticeable both in the rising limb and falling limb of the hydrograph. With the exception of baseflow, conditions in drainage basins are usually far from linear. Therefore, the rainfall runoff simulation model based on a linear reservoir that we just discussed is best applied to model baseflow. Also, as the model in its present form does not take account of the travel time of water through a drainage basin, the model should be used for small drainage basins. High groundwater levels or high water pressures at potential slip surfaces in the subsurface can cause hill slopes to become unstable and to slide down the mountainside. As the location of the water table may play a crucial role in the initiation or reactivation of landslides, modeling the groundwater level, for instance, by using a linear reservoir model, can be an important component of landslide research. Varved clays northwest of Gap in the French Alps, as shown here, consist of alternating thin layers of silt and clay. They are formed in former glacial lakes by variations in sedimentation during the various seasons of the year. A colluvial cover is an accumulation of sediment through the action of gravity at the lower parts of slopes. Van As and others used precipitation data over a 30-year time period and two linear reservoirs placed in series to represent the colluvial cover overlying the varved clays. Thus, the upper reservoir representing the colluvial layer is replenished or recharged by precipitation, whilst water outflow from the upper reservoir is taken as water inflow to the lower reservoir representing the varved clays. From this setup and additional work, Van As and co-workers successfully showed that landslide movements in varved clay areas northwest of Gap in the French Alps are mainly triggered by a maximum rise of the water in vertical fissures in the clays. Complete saturation of the clays is not necessary. As a very practical spin-off, their calculations also showed that drainage of the shallow, more permeable colluvial cover overlying the varved clays is a very effective measure to stabilize the deeper landslides. As interesting additional information, in 1990, work on the northern part of the Autoroute A51, motorway A51, linking Grenoble and Marseille, commenced. One of the originally outlined trajectories was via the area to the northwest of Gap. Another one via Aspre and Savonnon, right through the heart of the fieldwork area Pays du Breche of the first year Earth Sciences Utrecht University students. After much debate and quite some time, the route via the area northwest of Gap was selected. However, shortly after this decision was made, the project was cancelled at least for the time being, mainly due to the high costs of building an outer route through terrain prone to landslides. Now, 30 years or more later, part of the outer route in between Col du Fau and La Saulce is still missing. This sheet illustrates the workings of a slightly more complicated exponential reservoir model that is suited for modeling the contributions of through-flow and saturation overland flow to the discharge of small catchments. The figure to the left shows the core concept of the model. The rainfall rate minus the evaporation rate is taken as input I to the soil reservoir of a drainage basin. This soil reservoir or soil store loses water by through-flow. Above a soil layer that hinders vertical percolation, a perched water table may develop, the height of which is indicated by the water storage level H. If the quantity or volume of rain in millimeter causes the storage level H in millimeter to increase and then to exceed the water storage capacity Hc of the soil in millimeter, water is forced to the surface and will contribute to the stream flow as saturation excess overland flow. Kirkby and others used the following equation to model the through-flow outflow from the soil store in their store flow model. Qt equals Q0 e to the power St divided by m. St is the soil moisture deficit, in Dutch het bodemvochttekort, the difference between the amount of water actually in the soil in millimeter and the amount of water that the soil can hold, the storage capacity in millimeter. The soil moisture deficit has a negative value, but of course when the soil is saturated, then St equals 0. M in millimeter is a model parameter representing the soil characteristics. Combining this equation with the continuity equation delivers, after integrating and rewriting as a simulation equation, the following simulation equation. I delta t is the input during time step delta t. An explanatory file on the derivation of the store flow simulation equation is given on the online resource center or companion website of my book. Store flow essentially models slow through flow and saturation excess overland flow from an exponential reservoir that represents the soil of a drainage basin. The model in the form presented here cannot cope with Hortonian overland flow or pipe flow. Also, the model is intended for use only on small drainage basins where travel times are small. Store flow is a stripped-down version of the well-known rainfall runoff model, top model. In the figure to the right, one can see how the discharge varies with m. M within the exponent is in the denominator. If m is taken small, the rising limb of a modeled hydrograph will show a steeper rise and the falling limb a steeper decline, indicating that depletion of the soil reservoir is fast. Consequently, if m is large, the modeled hydrograph shows a slighter rise and fall, and the depletion of the soil store is slow. In the figure to the right, the portion of the runoff above the horizontal Q sat equals 10 mm per day line is overland flow. The antecedent moisture conditions in a drainage basin play an important role with regard to the height of the hydrograph peak and also the quick flow volumes. The figure to the right shows a more prominent and quicker reaction to rainfall as the drainage basin becomes wetter to the right. This is especially evident for the slower reacting hydrograph with m equals 50 mm. During the first rainfall event, no saturation excess overland flow is formed. During the second event, with the same amount and distribution of rainfall as the first one, some saturation excess overland flow is formed, whereas for the third event, a lot of overland flow is produced. For the second part of the third event, under very wet conditions, the M equals 10 mm and M equals 50 mm hydrograph peaks even reached the same level, but with the through-flow decline of the hydrograph with M equals 50 mm from this peak being slower. This figure clearly is indicative of the transparent results that may already be established from using a conceptual rainfall runoff model. The online resource center or companion website of my book contains an interactive spreadsheet on this exponential reservoir model StoreFlow. Exercise 5.4.3 is an added surface water hydraulics exercise that can only be solved when assuming a linear change of the discharge within a discrete period of time, pretty much in line with how simulation models work. Try to solve this exercise yourself first, but if not successful, you may want to study the separate video clip on this. The main focus of hydrology is on the terrestrial part of the hydrological cycle. Hydrology is concerned with the occurrence, movement, and composition of water below and at the Earth's surface. It plays a central role within the study of the Earth's system and touches upon many other areas such as climatology, meteorology, fluid mechanics, sedimentology, hydrochemistry, land degradation, ecology, etc. The accompanying picture is of the Roman bridge over the river Ouvèze in the southern French town of Vaison-la-Romaine. It stands firm, as it has survived severe floodings that have swept away more recently built bridges. In all respects, hydrology is a no-regrets study, as water and water-related problems are all important and will continue to be so. This sheet summarizes a large number of topics related to hydrology. The list of research topics in hydrology is even larger. To pick out just one, an important topic for hydrologists is climate change effects. This photo shows the launching of a drone to monitor the changes in time and space of a Himalayan glacier. The Himalayan glaciers are retreating at an increasing rate, which will eventually result in a water shortage for its downstream countries. This is an overview of the hydrology courses at Utrecht University in 2020. Course descriptions can be found in the Utrecht University Study Information System OSIRIS. You may want to halt this video to take a closer look. It is my hope that this course on physical hydrology has been a meaningful and pleasurable endeavor for you, and maybe a head start to get more deeply entangled with hydrology. For now, good luck with the remaining exercises and at the exam. And good luck with your studies.